Morning. I mean afternoon. Hello, hello. Hello.
We are timeless.
Afternoon. All right. Okay, so here we go. Today we're going to talk about 13.6 sigma notation. We'll start in about 30 seconds. So get your paper ready. Hello. All right. How are we doing? So let's start from the beginning. So have you guys seen this symbol before? This is a Greek letter sigma. Have you seen that before? If so, what does it mean? Any idea? What does it mean? Sum of. It's a sum, right? So this means sum. You're summing. What am I summing? I'm summing this thing. K squared plus 1. What is k? K starts from 1 and goes to 3. So it goes like this. So what does that look like? It's the same thing as, so when k is 1, this is 1 squared plus 1, right? When it's 2 is what? 2 squared plus 1, right? When it's 3, it's 3 squared plus 1. So you see how, like, I'm adding the same thing over and over again. The only thing I change is what k is, and it goes in order from 1 to 3. So 1, 2, 3. Okay, and you add them up, which will give you 17, I think. Right? 2 plus 5 plus 10, right? 2 plus 5 plus 10. 17. Okay? Let's look at it one more. So on the right side, you get that. So same thing. But instead, this time you're starting from 0 to 3. So it'll be 7. So it will equal to 7, 0 minus 3 plus 7 times 1 minus 3 plus 7 times 2 minus 3 plus 7 times 3 minus 3, like that. which is equal to -3, 4, 1, 49 times 30? I think 30. Yeah. Okay, 30. Pretty good with this. Alright, let's look at this then. So next one, it's so same thing. Plug it in, okay? The I here is not imaginary, okay? You notice that the I is the index here. So it's not the imaginary number I, it's the index I. So they just use that as a variable. Usually we don't do things like this because it's confusing as heck. But since they put it here, we'll just follow suit, right? Plus, I need more room, so I'll just add it like this. Oh. Which turns out to be, you add them up, -4, I think, right? Alright. Yeah, do the inside part first, right? I think it's -4. Is that right? Yes, verify. -4 is right. Okay. Alright. Number 4 is interesting. So, what does this look like? 1 over whatever k is, right? So, 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus all the way to 1 over n. And then it keeps going, right? There's no end to this. How do I know there's no end? Just look at this. Goes to infinity, right? So, that's what it looks like. Okay? So, let me ask you an additional question. Didn't ask you about this. Well, they kind of did, but does this converge? Does this converge? Converge meaning that does it have an answer? I mean, the terms, each term is smaller than the previous term, right? But does this converge? Type Y or Y not? Okay. Type Y or Y not? Does this converge? Looks like we need a calculator's help. So usually, right, like if you converge, then the more you add, the more it's closer to a number, right? So if you look at, like we use calculator, so 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. Okay, well, I did 4 terms. It's 2.08, okay? I'll add more. 2.45. Okay, I'll add more. 1 over 7, 8, 1 over 9, 2.82. So it's increasing, right? You see that? It keeps increasing and it's increasing more and more. It's not stopping, right? Like when you're adding things like, another example, if you have 1 plus 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16, something like this. This converges, right? This is called infinite geometric series. R is 1/2, so we know eventually this is going to equal to 2. You don't believe me? Well, look. If you do that instead, then it will be 1 over 2 plus 1 over, 1 plus 1 over 2 plus 1 over 4 plus 1 over 16, 1 over 8 plus 1 over 16, see 1.93, and you keep adding, right? Plus 1 over 32, 1.96, oops, plus, oops, 1 over 64. It's never going to be over 2, right? So it's going to be approaching the 2. So what is the main difference between the two? What is the difference? How come this one, when I add, it doesn't get bigger infinitely, whereas this one diverges? This is converge. Why? What's the main difference? Converge to 2, right? These are very classic examples of a divergent and convergent series that does not have necessarily, like they look very similar, right? Very similar. Anybody wants to get a tackle on like the main difference if you look at these two series? What makes the difference of converging or diverging? This is almost like calculus C area, but I want to give you a little bit of priming. Why does the top converge? Why does the top diverge and the bottom converge? Okay, so you're saying that this is exponential decay, and this infinite geometric series, so obviously this one converges. But what I'm asking is, this one versus this one, right? They're both decreasing, right? When you're adding, your number that you're adding is decreasing for both of them. How come this one converges, that one doesn't? Okay. So notice I said that you're adding less and less, right? Is this even true? Are you really adding less as you go? For this one you are. How do I know? Well, check this out. This starts with 1, right? Everything I add after 1 is less than 1. What I mean by everything is everything, okay? Everything from here all the way down is less than 1. Notice that? When you add them all together, it's less than 1. Meaning that it will never add more ever than what you already have. Everything less after 1/2 is less than 1/2. 1 4 plus 1 8 plus 1 16 plus everything after that together is less than 1/2. Everything after 1 is less than 1. Okay? But if you look at this one, what's 2/3? What's 1/2 plus 1/3 plus 1/4? Just look at these three. Okay? 1/2 plus 1/3 plus 1/4. 1.08. This part is already greater than 1, which means the more you go, actually you're adding more and more. You're adding more than what you had before. Whereas this one, you're adding less no matter how the series progresses. You think you're adding more terms, but in reality, whatever you add here is just smaller than what you had before. Okay? So that's the main difference why one converge, one diverge. This is a very famous series called Harmonic Series. And obviously this is infinite geometric series. Okay, these are very classic examples. If you're really interested in math and you decide to take calculus later, could be helpful. Okay. Does that kind of make sense? Alright, well, let's go back to the main idea of the day, which is sigma notation. So let's review real quick. So k equals whatever this number is your start. Okay? This is your end. We'll put a number here. And then this is your expression, whatever that means. And the k is your index. Okay? Cool. So, I want to go over a few things. So, here. Let's look at this. So, if I have k equals 1 to 100 and expression is 1, what am I adding? When k is 1, my expression is 1. When k is 2, my expression is still 1. When k is 3, my expression is still 1. Because there's no k, right? So there's 1 over and over again. How many 1s do I get? 1 to 100, so there's 100 1s here. So answer is 100. Okay. Similarly, on the right side, if I'm going to n, what would the answer be? I get 1 plus 1 plus 1 plus all the way to 1, which is n 1s, which end up being n times 1 is n. Cool. All right. What now? Then, what about this one? I from 1 to 100 of I. That means you're doing 1 plus 2 plus 3 plus 4 all the way to 100. We did this problem, didn't we? This is a triangular number or arithmetic series. Remember how we do this? This is a trapezoid rule, right? 1 plus 100 times 100 divided by 2. 100 times 1 plus first plus last times how many terms divided by 2, right? Which in this case was 50-50. Right. So, here, it would be a same thing, 1 plus 2 plus 3 plus all the way to n. So if you want to put in the formula, it will be n times n plus 1 over 2. Okay? Lock these down. Alright, we're going to use these later. There's one more I want you to look at is when it's I squared. This one is not in the notes, so I'm going to add this part. So sigma I from 1 to 100 of I squared, which is 1 plus 1 squared plus 2 squared plus 3 squared plus 4 squared plus all the way to 100 squared. Okay? We don't have a tool to do this, so I'm going to tell you the equation first, and then we can work on that. Okay, so 1 to n of I squared is going to equal to n plus 1 to n plus 1 over 6. Okay? Keep this in your mind. How do you prove this? Well, there's two main ways to do it. One is called math induction, which you may or may not learn in the end, math induction. The other one is called binomial expansion. If you're interested in this, just look for proof for sigma n I square. They have the whole proof. Usually the people prove it with number 2. Binomial expansion. What is binomial expansion? Binomial expansion is basically k plus 1 cube, for example. how do I expand this? Equal to blah blah blah. Then we have the like age. I don't know if you remember this. 3 choose 0, k to third power plus 3 choose 1, k squared plus 3 choose 2, k plus 3 choose 3. That's called binomial expansion. I think we did that like maybe, I don't remember when, but it's in algebra 2, something like that. But anyway, binomial expansion. But if you're interested in how to prove that, you can look it up. Okay. But the actual application of it, I'm gonna use it here. So I'm gonna just plug it in. So it's 100, 100 plus 1, 200 plus 1. Okay. So you multiply this out. It's gonna give you 100 times 101 times 201 over 6. So I get 338,350. Okay. Now, why is this good? Well, can you flip it over into a blank spot? I want to go over one thing. So flip over to take a look. I want you, so for example, if you get something like this, from k equals 1 to, let's just say, 20, okay? And then the expression will be 3k squared plus 4k plus 1. Let's just say that, okay? Say that. How do I do this? Well, you can plug in 20 times and add them up. That's possible. But since we know the formulas that we had from the previous page, we can split this. Because multiplying by 3 will happen every time, and adding is commutative, meaning that you can add in any order. I'm going to organize it by splitting the sigma. Okay, so it'll be sigma k from 1 to 20, 3k squared plus sigma k from 1 to 20, 4k plus sigma k from 1 to 20 of 1. Does this part make sense? Basically, what I'm doing is, since I'm going to add these things 20 times, right, from 1 to 20, I'm going to add all the things with 3k squared first, and then all the things with 4k, and then all the things with 1, from 1 to 20. Okay? Does this operation make sense? Splitting it. Okay? And then the next thing would be, okay, everything is 3k squared, right? 3 times 1 squared, 3 times 2 squared, 3 times 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, etc. They're all multiplied by 3, so I'm going to factor this 3 out. So it's going to look like this. And pull them forward, like that. Okay. Pull the 4 out. And then you don't have to pull anything out here because it's already 1. Okay. All right. So now you can calculate. How do I calculate? I'm going to use the formula I had before. I'm going to do this part. Okay. So 6. This is n plus 1, right? But it's 20 for n now. 20 plus 1, 40 plus 1, right? Because it's 2n plus 1. Plus 4 times. I forgot to put the k there. I'm missing a k here. Yeah, the k still stays. And n plus, oh, okay. N is 20, right? So it'll be 20. Yeah. 20 plus 1 over 2. Plus, this is 20, right? Because we had this 1 20 times. Alright, so time to pull out your calculator. So let me do some cancellation first because I can. 3 and 2, right? This and 10, right? This will be 2, right? Okay, so it will be 10 times 21 times 41, 8, 6, 10, plus 40 times 21, 840, plus 20, which is 9470. Okay. So the process, first you split the sigma. Okay, initially you split the sigma. Once you split the sigma, you pull out the coefficient. Once you pull out the coefficient, then you can apply the formula we had before. And once you get that, you can calculate it based on your n. Okay? Do you guys get all the equation down already? Should I flip it back and show you that, or you're okay? Is it okay? Alright. Nobody said anything, so I assume it's okay. If it's not okay, let me know, okay? Next page. So, write the following in sigma notation, then find a sum. So, what does that mean? It means like this. Alright, so this is already sum, right? Sigma, sum. So, sigma. What kind of sequence am I adding? What kind of series am I adding? I'm adding 2, 8, 14. What kind is this? Write in the chat. What kind is this? 2, 8, 14, etc., etc. What kind of series is this? Arithmetic, geometric, harmonic, anything? No idea? Arithmetic, thank you. Thank you, Allison. Thank you, Olivia. Alright, so it's an arithmetic series. So what your expression should be arithmetic, right? Arithmetic means I can use arithmetic sequence. So 2 plus in this case, will be k minus 1 difference is 6. Okay? Some of you might ask, well, shouldn't you do the series formula? Well, notice that the series part is covered by the sigma. So you have to, if you want to use sigma notation, then you will have to add sigma of what expression am I adding? I'm adding an arithmetic sequence, right? So I'm going to use this formula. And I'm adding into 100 terms, so this will be 100. Okay, so check if it makes sense. If you plug in 1, you'll get 2. Plug in 2, you get 8. Plug in 3, you get 14. And you keep adding by using the sigma sign. Okay, because it's sigma notation and we want to find a sum, there are 2 ways to do this. One way is you actually just do the formula, find what the last term is, right? So your last term is going to be first plus last, right? First plus last. Last is going to be, so it's 100 terms. You times 100, so 99 times 6 plus 2 is going to be 596 and over 2, right? That's one way to do it. That's 50 times 598, which will give you 29,900, right? Does that make sense? So that's one way of looking at it. Alternatively, you can split it. Okay, simplify and split it. So I'm going to do, this will be what? 6k minus 4, right? Something like that. and then you split it like how we did it before. So 6k, k from 1 to 100, minus 4 sigma 1 to 100 of 1, right? Split it, right? Split the minus sign, split the sigma, pull out the coefficient, and I'm going to do the formula. N times n plus 1, right? So it's 100 times 100 plus 1 over 2 minus 4 times this part is just 100 because 1 times 100, right? Okay. And then you're going to get 3, so 300 times 101. So it'll be 300 minus 400, which will also be 29,900. Okay. So either way, whatever method you choose to do should give you the same answer. Okay. All right. So similarly, if you look at the right side, okay, it's the same exact problem, but what if you just want n terms? If you just want n terms, then you have to do it like the same way, but you don't plug in the 100, okay? So if you compile this over, when you plug in 100, don't plug in 100, you just plug in n. So 100 is n, 2 plus n minus 1, 2 plus, no. First plus last, right? First is 2, last is 2 times 2 plus n minus 1 times 6. Okay, that was the last term. And then divide by 2. Okay, simplify this, you're getting the answer. Which will be, notice that this is your Tn, okay? This is your Tn. And this is your T1. Right, T1. T1 plus Tn times n divided by 2, right? Okay, now the rest is simplifying. 6n minus 6 plus 2 plus 2, so plus 4, so 6n minus 2 over 2. So that's going to be 3n minus n squared. No, 3n squared minus n, I think. Does that look right? You can use the same way to find it using this one. There'll be everything here will be in n, and then you just subtract it through. You'll get the same answer. Okay, they're interchangeable. Number 8. Use sigma notation. So what kind of series is this? 1, 3, 9, 27, 81. How can I write the expression? There's 5 terms, so I'm going to do 1 to 5. Okay. How does this work? What is this? 1, 3, 9, 27, 81. Geometric is correct. Rate is 3. So remember, geometric, you do first term times rate to the n minus 1 for the expression. So it looks like that, right? So that's your sigma notation, and then you just add them up to find the answer. This one you don't even need to really calculate it, but you can also use the formula for geometric, which is first term 1 minus r to the n. Okay, let me remind you so that you remember what you're doing, okay? I feel like sometimes I don't write the formula down and you forget what the formula is. 3 to the n over 1 minus 3, which would be, to the 5th power, right? 5. Right. So that would give you 121, I think. Is that right? 121. Alright. Alright. So try number 9. Number 9. Okay, see if you can write it out. And while you try, let me take some attendance. So if you're here, just say you're here. All right. Any idea? So what kind of series is this? In other words, how do I write an expression for this? Well, first of all, I'll start with 1, okay? Usually because it keeps going, so we'll put infinity here. Right? But this is geometric, right? Rate is half. So you start with 48 times 1/2 to the k minus 1 power, just like how you do with geometric sequences. But the sum is taken care of by the sigma, so you can leave it like that. Okay. Hey, remember how to do infinite geometric series? Do we have a formula for this? Isn't it S is, because your R is less than 1, we talked about this. R is less than 1, this part will go to 0. So it will be T1 over 1 minus R. Since R is less than 1, the more you multiply, the more closer to 0 it gets. So all you have is 1 minus 0 here, so you're going to get this formula instead. Then you just do 48 over 1 minus half, which ends up being 96. Yeah, Brandon, you're correct. So if you want to start at 0, then it will just be k. Okay? You can fix your indices. You don't have to start at 1. It's just I want to stay consistent with the sequence formula we had before. That's why I start with 1. But if you start with 0, then this will just be k. Right? Because you just want to fix your first term. The pattern is still there. Okay? Does that make sense? Last question. So you want to write in sigma notation. So first of all, is it arithmetic or geometric? This one is a plus 4 seems to be arithmetic. So I'm gonna write in arithmetic. Okay, sigma. Arithmetic will be 3 plus k. I'll use k. So k minus 1 difference is 4, right? So that's what it looks like for now. Right. K, I like to start from 1. You can start from 0 if you want, but you have to fix your expressions to make sure the first term matches up. The problem is right now, how do I know what this is? Well, that's the index that I have to end at, right? So to know what that is, I need to know what? When is this expression going to be that number? Okay? Because that's the last term, right? That's what I'm going to end. So I'm going to set them equal. 3 plus k minus 1 times 4 equals 715. move it over. K minus 1 times 4 is equal to 712. Divided by 4. K minus 1 is going to be what? 178. So K is 179. So you put 179 here. Alright, that's what you want to end. Say that again. When you are trying to find the end index, okay, the index that ends, you want to make sure your last term is equal to the expression. That way you know what the index needs to be to end. Does that make sense? That way when I plug in 179 at the last term, I would get 715. Right, 179 minus 1 times 4 plus 3. That will give me 715 when I plug it in. Okay? So I'm going in reverse. Alright, so then once you get that, then you can just calculate. This is arithmetic, right? So 179 terms, n is 179. First plus last, right? So 3 plus 715 over 2. Okay, which will be... oh, they didn't even ask for the answer, but we'll calculate it anyway since we like to. 718 divided by 2 times 179. 64261. Okay. Alright. How good are we with this? Gonna get a 1 to 10. This is the last instructional thing that we're gonna get this year. And possibly with me ever. Next week we're gonna have a small assessment. We're gonna do it in class. It's not gonna take long, and that will be the last thing we do. And we can chat a little bit if you want, but that's the plan. Okay. Oops. Alright, not bad. 8 to 10. I would say it's okay. So homework. So homework is the review page. Chapter 13 review. This is the last page of your packet. So if you haven't printed this out yet, I don't know why you haven't, but you know the school year's over. So I also have this on Google Classroom. I can't spell Google. Google Classroom. This is due this Sunday. Okay. Yeah, just resubmit it. It's fine. Resubmit it. The assignment's not closed, so you can resubmit. It's fine. So that's all. Any other questions before we say goodbye? I don't know if yeah. For the people who are graduating, congratulations. And I think this is your last class, right? Next week you won't be seeing me. So good luck to all seniors. And yeah, hopefully you get to shine in your life. Yeah. Any last words before we go? Well, if you have any more questions, tomorrow. No, it's not. So originally the chapter 12, 13 test is going to be tomorrow, but I feel like why not just move it into... Okay, if you're a senior, you're done. Okay, you don't have to take the test. All right. The test is not even like a real test. It's like an assessment for me to know how much you know. So it's probably going to be, I mean, it's going to be just like participation kind of thing. So we're just gonna, next week's class, we're gonna do it in class. Okay, so kind of like classwork almost, but it's like, I'm not gonna tell you what to do, but that kind of thing. Okay, so we're all gonna be in class doing this thing together. Together meaning like at the same time, but we're not gonna, it's not gonna be affecting your grade in a huge way. As long as you come and take it, you'll be fine. Okay? But if you're a senior, then congratulations, you're done. You don't have to come because you're not. It's in class, right? Since your class is done, you don't have to come. But if you want, you can. I don't mind. I don't mind having you one more time. All right. Good to go. This is your homework, by the way. If you haven't seen it, it looks like this. Okay? The whole page. All right. But even those who are graduating, you have to do this assignment. Okay? This is the last assignment of the year. Thank you, guys. You're welcome. All right. Goodbye. Let me play something so that it feels like it's over. Have a good day. Bye-bye.